Problem 18. I'll skip the reading of the beginning of the problem, but let's get to the main point here. Find the rate of change of the temperature at a point 110 in the direction of the vector 1, 1, negative 1. Okay, this is just kind of changing the wording a little bit, so you know that rate of change essentially means derivative, the instantaneous rate of change. So ultimately this is still a directional derivative problem. Same idea, because you're trying to find the rate of change, which is the derivative at a point in a certain direction of a vector. So it's just directional derivative. So here's our function, which means we're going to need the gradient. It's kind of on two lines there, but it's actually named W. That's why I'm using W, but that's not critical. The letter, but the partial derivative is, of course. So the partial derivative, there's two y terms. So, two x terms. There is two y terms, but so it'll be x will be 1, x will be 1 with the derivative. So you have y plus 2z. Pretty easy partial derivative. The y terms, both y's go away, so it'll be x plus z. And the last two have z terms. So it'll be, there goes the z, so it's 2x. There goes the z and y, 2x plus y. So the gradient evaluated at the point 110. Plug it into this. Real easy, you'll get 113. So now all we need is the unit vector of the direction vector. Always remember we have to convert the given vector to a unit vector. That's usually the most common mistake that people make with directional derivatives. They're not difficult, but you have to remember to make that direction vector a unit vector. And I didn't show the calculation of the magnitude, but I imagine at this point you should be pretty proficient at it. It's not too hard to figure out that the magnitude of vector v is square root of 3. So the unit vector would be the vector divided by its magnitude. So it's that 1, 1, negative 1 all over the square root of 3. So I kind of then just wrote it like this, 1 over square root of 3. So it'll be this gradient we got up here, dotted with this. So if you leave the 1 over root 3 alone, you can just dot the integers. So it'll be 1 times 1, 1 times 1, that makes 2. 3 times negative 1 is negative 3. 2 plus negative 3 is negative 1. Then we can multiply it by that constant right there. And it'll be negative 1 over root 3, which is perfectly fine. But, there's a mistake here. All right. That should be negative root 3 over 3. Okay. All right. So I rationalized the denominator, but I forgot to change the sign. Okay. Just in case answer choices look that way, they might be rationalized. Okay. Now the maximum and minimum value of the directional derivative at a point is going to be the magnitude. The maximum value will be the magnitude of the gradient at that point, and the minimum value will be the negative magnitude of the gradient at that point. So let's see what we got here. So here's our function. Let's get the gradient. So technically we're not even finding the directional derivative. This will always be true. But the maximum min will always, at a point, will always be the gradient. That'll be the maximum and minimum direction values. So derivative of this one's easy, 4x, and then negative 6y, 4z, and then the gradient at 1, 2, 1. So you just plug it right into here, will be 4, negative 12, 4. I went ahead and pulled a 4 out there for taking the magnitude purposes. That way I'm just taking the magnitude of 1, negative 3, 1, which will be the square root of 1 plus 9 plus 1. So it's 4 square root of 11. And then the minimum value is negative 4 square root of 11. And they're both, and the maximum will be in the direction of that gradient, 1, negative 3, 1. And then the minimum will be going in the opposite direction of that gradient, just the other way. And see, I talked about this in my notes for this section. So that means if you just went through and actually picked a point, or you could even use that point, and just use some other random direction vector, you can make one up. And if you calculate the directional derivative, the value for that directional derivative will be numerically between -4 root 11 and +4 root 11. So that's basically the bounds of what the value of the directional derivative can actually equal. I believe, like I said, I showed that in my notes, where I did a directional derivative and said, hey, look, it's between those two numbers. Alrighty, number 20. Equation for the tangent plane to the surface. Sorry about that. That kind of looks bad right there. I don't think you have to worry about that for test questions. It's when I converted these files over to this format, it sometimes messes up the, like this. Probably if you look at your original file, it doesn't look this bad, so just work off that anyway, the file of the questions and with the answers themselves, so you'll know what's going on. Okie doke. Tangent plane. All right, the one of the features about the gradient is it gives you a normal vector to a surface at a particular point on that surface. It gives you that normal vector. So the tangent plane, is going to kind of touch the surface at a point, and only that point in the immediate area. It's the three-dimensional version of a tangent line, back in Cal 1, where it's only touching the line in the immediate area. Well, this plane is going to clip it right at that point. So, so your normal vector then comes from the gradient. And so basically it's just going to be following the equation of the plane. Also it's asking for the angle of inclination. So we'll take care of the equation first. All right, so let's get the partial. So x squared will be 2x. There's no x here. And bring this over like I did right there. Where we had another problem where this happens. We want to put it in this implicit form right here. That just basically means there's no numbers in there, but if there were, it wouldn't matter if if you set it equal to 0 or left the number alone. The important thing is you get all the variables on one side. So you bring the 6z squared over. It doesn't matter if there's 0 there, that doesn't matter, or 2 or whatever. Anyway, so x squared will be 2x, and then the minus 8xyz will be minus 8yz with respect to x. With respect to y, we'll have minus 8xz, and y squared will be 2y. Then with respect to z, we'll have minus 8xy, and then minus 6z squared will be minus 12z. So if you plug the point 1, 1, 1 into this gradient vector right here, you'll get -6, -6, -20. Now, I wrote it in the standard form, which is the A, goes way back to we did equation of planes back in chapter 11, is basically, A times x minus x0, y times y minus y0, and then plus z, c times z minus z0. So here's what it would look in that form, as which I have it right here. Now, I worked it out. I didn't put it in the answer right here, but I also worked it out because it's very possible that the answers in a multiple choice format might be in general form. But that's just distributing the terms. So long as you're okay, here's the starting point right here. We start with this because our point's 1, 1, 1, so they'll all be x minus 1, y minus 1, z minus 1. So I distributed it out. Now, and then I came down here. And this is where you would just be kind of looking to see what the answers look like. Now move the 32 over the other side, which would be negative 32. Now keep in mind, you might look at this, and any answer choice you see that's the opposite of those answers would be the right answer, because you can flip all the signs by multiplying by negative 1. So that's easy to reverse all the signs. So you might be looking at this answer and going, hey, I can't find that answer choice. Multiply them by negative 1 and reverse all their signs and see if that's correct. This one, I hope this wouldn't be done, but this one's also divisible by 2. So, but I don't know if hopefully nobody would resort to that. But you could reduce it by a factor of 2 and have 3x plus 3y plus 10z equals 16. Angle of inclination. It's the formula for the angle between two vectors, except we're not finding the angle between two planes. We're finding the angle, the plane goes up from the xy plane. And we're finding then so to find the angle between one of the planes being the xy plane and the plane we're given, is you find the angle between their normal vectors. Well, for the xy plane, we always use k down here. Because k is going up the z-axis, 0, 0, 1, and it would be normal to the xy plane. But technically, just to let you know, it could be 0, 0, 1, 0, 0, 2, 0, 0, 3, whatever, and it would still work. But 0, 0, 1 is good because you may recall the regular angle between two vectors. Well, let's say two planes in general. You had an n1 and an n2, and an n1 and an n2, and it looks like something's missing on the bottom here. Like, where's the other magnitude? So really the formula normally would have the magnitude of k down here. But if you're just using k, 0, 0, 1, the magnitude of k is just 1, so it goes away. So that's why you don't need all that. So all you do is take your normal vector right here, negative 6, negative 6, negative 20. You dot it with 0, 0, 1. And you'll get negative 20. Now this has absolute value. This one's absolute value because it's important that we're looking for the shortest angle to the plane. So it's going to be something between 0 and 90. So it's not going to be between 90 and 180. Whereas way back when we were finding angle between two vectors, yeah, we allowed that. There wasn't a absolute value in that formula, so therefore, the answer could be 120 degrees or something. Oh, here it mentioned, should be in degree mode. So so that negative 20 then needs to be positive 20. So basically you're finding the inverse cosine of 20 over square root of 472, which is the magnitude of this normal vector right here. Yeah, I guess I could have pulled out a 2 there, but that's okay. You're just plugging this in the calculator anyway, so you can see that positive 20 is entered in the calculator for the absolute value part, and I am in degree mode. I checked, and yeah, roughly 23 degrees, or however many decimals they round it. You should have no problem with that. All right, number 21. Parametric equations for the normal line to the surface. Okay, that means if it's a normal line to the surface, the direction vector of that line will be the gradient, because as I've mentioned before, the gradient is the normal line to the surface. So all we have to do here is get the gradient and then use our parametric equations, which I posted right there from a long time ago, and it's no problem. So the gradient's going to be 2x plus 7yz, 7xz plus 2y. Once again, you move this term over and make it negative, so negative 9z squared. That way it's in implicit form. So it gives me 7xy minus 18z. Put in 1, 1, 1, 9, 9, negative 11. So that's your ABC, your direction vector for that normal line. So we have, the point is 1, 1, 1. There's 1, there's 1, there's 1. And then, so now we have 9, 9, negative 11, so it's 1 plus 9t, 1 plus 9t, 1 minus 11t. There we go. That's not too bad. Find the differential. Let me see this. Okay. Let's see. All right. So it's w with respect to 3 variables. So the differential is just going to be where you just have, it would be dx, dy, dz form. So we're taking 3 partial derivatives with respect to x. So the y will sit there. The derivative of sine is cosine, so you'll have x plus z on the inside. And then you take the derivative of the inside by the chain rule with respect to x. So the derivative will be, so that's why I wrote that 1 right there so you could see it. The next one, respect to y. The y just goes away. Its derivative is 1, but you don't take the derivative of sine. Don't make that mistake. So this one, this term, sine of x plus z is just a constant multiplied times y. So it just stays there like that. So we don't take the derivative of it because there's no y in there. Now, the last one will be similar to the first one. The y will sit there. We'll take the derivative of cosine of x plus z, but then you're taking the derivative of the inside with respect to z, so it's 1. So it happens to be the same as the first term, but that's only just because of the coincidence that the derivative on the inside part is 1 for both x and z. So that's why they're identical. Now here's a total differential calculation. And the differential, there's 2 that we calculate the change, and then the actual dz is the differential. And remember, these should be close to each other. You know, there's no exact rule for how close, but if they're way, you know, if you got 1.456 here and got like 4.5 for the other one, you're pretty far off. So something went wrong. So the actual change is we just take f of the second point minus f of the first point. So down here in this calculator box, you can see, so really all I did is plug it right in there. So 3.2 squared times 1.9 minus 3 squared times 2. I got 1.456. Now, so for the total differential, you have to, you know, do basically dz will be fx dx plus fy dy. So the derivative with respect to x then will be 2xy. Respect to y will just be x squared, and the dx and dy represent the change in x and the change in y. Could be positive. You just take the way you figure that out. It's real easy. Just take the take the first second x value minus the first x value. So 3.2 minus 3 is positive 0.2. 1.9 minus 2 is negative 1. So remember, they can be negative. So that one, the y went down. So we have 2 and times x, and you always use when you're plugging in x and y into the differential equation, you always use the starting point. So 2 times x is 3 times y is 2, dx is 0.2. X squared is 3 squared times dy, negative 0.1. I didn't put that one in the calculator, but that one's pretty easy, because this actually is showing the numbers. I didn't actually show the numbers up here, but so it's pretty easy to calculate. You get 1.5000. I just used, it says use 3 decimal places for each, so added the 2 zeros. All right, that's the differential. Here's another differential. Not quite your typical looking differential problem. I'm treating, so R is a function of V0 and alpha. Those are 2 variables. It may not matter, but I'm treating the V0 as X, and the alpha is the Y, although it probably doesn't matter that much. All right, so let's see what the derivative. So now we're taking the derivative with respect to V0. So you bring down the 2, that makes it 1/16 V0 to the first, and then the sine of 2 alpha will just sit there, dV0. So let's see how I did that first, so I treated that as X. Yeah, I don't think it would have mattered either way. Next one is, so the V0 squared is now a constant. So it's 1/32 V0 squared. The derivative of sine of 2 alpha with respect to alpha. Well, of course, the derivative of sine is cosine, but we have to remember the chain rule to take the derivative of the inside. So the derivative of 2 alpha is 2. And so it's 2 cosine 2 alpha. All right. D alpha. So let's look at the values. Let's see. So our starting point is 400 for V0, and it's 30 for alpha. So that's what we'll put in for values. Now we need to know the finishing values to come up with our differential changes in X and Y. In this case, V0 and alpha. But V0 is going from 400 to 395. So that's where the negative 5 is coming from. That's your dV0. Alpha is going from 30 to 31. That's a +1. So that's where these 2 numbers are coming from. And we plug in, like I said, just like before, we plug in the starting values. So just plug in the 400 for V0. Make sure you're in degree mode here. There are 2 alpha, so they're going to be 60 degrees. 2 alpha 60, 2 alpha 60. And then the V0 is 400. Just kind of plug all that in there and kind of crank it out. And I got roughly 4892 as the rate of change for the range based on those values. The approximate rate of change. That's what differentials are doing. They're approximating the actual rate of change. I guess we could have tried to calculate the actual rate of change just to see how close this answer is, but that's okay. Number 25. So now we're getting into finding the extreme values. Mins and maxes using the second partials test and all that good stuff. All right. So we have to get obviously the first partials to get the second partials. We have to get everything here. So we have to use the first partials to get the critical points. All right. So let's see. Pretty easy there. 2x plus 2. That's 2y plus 8. The fxx partial will be 2. Fyy partial will be also 2. And then the fxy partial will be 0. You take either order. The y partial of this will be 0. So So we need to solve this kind of as a pair of equations, but they don't, since there's, there's only one variable in each one, they don't exactly interact with each other. So x has to be -1 and y has to be -4. This one's kind of a little bit basic one numerically. I would expect, definitely more challenging than this on a test, but it's a good start. So -1, -4 is the only critical point. So we're trying to figure out if it's a relative max, min, or saddle point. All right, there's the second partials test. Yeah, and these second partials don't even have variables in them, so usually a lot of times they'll have variables, so you would actually plug in, the x and the y into the variables, but there's no variables here. Yeah, this one's pretty trivial here, but it's okay. That's all right. So fxx is 2, so we're using this formula right here. Fyy is 2, fxy is 0, 2 times 2 minus 0 squared. 4 is greater than 0, of course. So if d is positive and fxx, which is positive 2, if that's positive, if those are both positive, you have a relative min at that point. So you have a relative min at -1, -4. All right, so there we go. Let's take a look at this function. Well, this one offers a lot more excitement here, doesn't it? Looks like we're going to get quite a few critical points on this one. Could be exciting. Fx partial will be 3x squared minus 300. Fy partial will be 3y squared minus 75. Fxx will be 6x. Fyy will be 6y. And the mixed partial will just happen to be 0. Obviously, don't assume it's going to be 0. It just happened to be two problems in a row. Now, once again, these variables don't interact with each other. Where there's like x's in both equations and y in both equations, where you're looking at some sort of substitution or elimination type technique. But what's important in this problem is that, okay, this equation ends up being x squared equals 100, which you have to realize means x is plus and minus 10. Don't forget that. Same thing here, you get y squared equals 25, gives you plus and minus 5. Now, that means the x's and the y's, you have to take every combination of these pluses and minuses as critical points. So, -10, -5, -10, +5, 10, -5, and 10, 5. So we have to test all these. Okay, I kind of skipped some of the work here, but, you can always ask me if you're not sure. But anyway, there's from up here, there's the D equation. It's not too hard to, even without showing the work. I'll sort of tell you the way I looked at it. Okay, so there's what we're starting with right there. So we have this. So if you put in -10, -5, obviously the minus 0 squared, you just ignore. So real quickly, I could look at this because we don't need the actual number for D. Remember, actually, if you get the number, that's fine. We just care about the sign of the number. Is it positive or is it negative? So if I put in -10, I got negative, 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 positive. That's how I quickly got that. So in other words, I didn't really do any calculations here. And in this case, the fxx right here would be -60. It'll be negative. So D is positive, fxx is negative. We have a relative max. And we have for -10, +5, D will be less than 0 because you'll have negative times positive, and when D is negative, it's game over, it's a saddle point. Same thing here, positive and negative will multiply together to be negative, another saddle point. And then 10 and 5 both positive, makes that positive, but fxx will be positive this time, so you have a relative min. So we have a relative max at -10, -5, saddle point -10, 5, saddle point 10, -5, and then a relative min at 10, positive 5. And there we have it. So there were a lot of critical points for that one, but it wasn't too bad. This one. So here's the function. So the first fx partial will be 4x cubed plus 4y. Fy will be 4x plus 4y cubed. And then the fx to f double. So you take this next partial. Yeah, sometimes you see in my notes the way I did these, and you do them the way you want. You might not want to. I just kind of did it for space in these problems. You might not want to stack it down. I did some where I split the fx and the fy apart, so I wouldn't make the mistake of this way. You have to be careful. Is that when you find the fxx, you're not taking the partial of the line above it. It's 2 lines above it. So long as you're careful there, that's okay. But and I usually try to be careful myself. But so the fx to fxx will be the x partial of the top one, which will be 12x squared. And then the y partial of this one of fy will be 12y squared. And then I can take the y partial of the top one to get the mixed partial, which will just be 4. And then so now we're going to get the critical values. So I got all kinds of arrows drawn here. Now, so here's these two equations set equal to 0. Elimination's not really going to work in this problem. You're not going to be able to use elimination, so it's going to have to be substitution. So I could have taken either equation. And, it's either one. I would have been fine. I took the top one. I guess I don't know why I didn't. Well, okay. That's all right. Seemed like the arrow should have gone the other way, like from top to right here. But anyway, so you take that top equation, solve for y, you'll get this, negative x cubed. Then you plug it into the other equation, the bottom one. So I have 4x plus 4 times negative x cubed, which will give me 4x minus 4x to the 9th equals 0. Factor out of 4x, and you have 1 minus x to the 8th. And then set these equal to 0. You got 4x equals 0. 1 minus x to the 8th equals 0. And you really don't have to do anything too fancy on this, because it looks like, oh, it's going to be terrible, x to the 8th. Mainly because we're not extracting any imaginary solutions from this, so we don't care about imaginary roots. But anyway, x to any even power, in this case it's the 8th. If you take x to the 8th equals 1, it'd be the same thing for x to the 12th or x to the whatever equals 1. The only two solutions are going to be plus and minus 1, because you take a plus or minus 1 and raise it to any even exponent, they'll both be positive 1. Yeah, so this x to the 8th power would only be difficult if we were trying to get imaginary roots in there. So let's say if it was an odd power, so it was like x to the 9th. Well, x to the 9th equals 1 is only going to have one answer, which is 1. If it's equal to negative 1, it's only going to have one answer, which is negative 1. But even power will have 2. So you have these three x's, and we you could plug them back in, but that's the whole idea here. You've already got y in terms of x. So if you put in 0 and plus and minus 1 into that negative x cubed, so 0 will make that 0. You put in negative 1. Negative 1 cubed is negative 1, but it becomes positive because of the negative there. Then when you put in positive 1, it becomes negative. So you have 0, 0. Negative 1 will become 1, and then 1 will become negative 1. Okay, so now that we got through the algebra there, we're ready to plow through the rest of this. That can sometimes be the most challenging part. So here's the setup for the D from up here, that value D. Test these critical points in any order. Just be careful when you're looking at answer choices, though, what order they're in. All right, let's do 0, 0. So you put in 0. That's going to be, now this time it's going to matter here. Earlier we had a 0 for the last example. That's a 4. So we're subtracting 16. So we have to be careful. So actually I worked the numbers out over here. for you. You can still do it if you're careful without working the numbers out, but you might want to just to be on the safe side. But this one I didn't really need to, because I knew that was going to be 0 minus 16 was going to make it negative. Automatic saddle point. The next one, you put in negative 1 and 1. They're both going to be positive 12. And I could look at that and go 12 times 12 minus 16 is for sure going to be a positive number. But go right ahead and work it out if you need to, no problem. D would be positive. Fxx would be positive, because it'd be 12. You got a relative min. 1, negative 1 is going to be the same thing. Mainly because you have an x squared and a y squared, they're all going to turn positive anyway. So you have a positive value for D again. And Fxx is positive, so you have a relative min. So you basically have a saddle point and 2 relative mins. There's the second parcels test again. Number 28. A box with no top has a volume of 32 cubic feet. What's the least amount of material, surface area, required to get that volume? I already have the answer here because the answer was wrong on the key. I believe there's a question like this on the quiz. It was kind of the opposite idea, where you're given this surface area of the open box as a number. That's your constraint, and then you're maximizing the volume x times y times z. So you would say maximize v equals x, y, z, subject to this adding up to whatever the number was in the problem, in the quiz problem. I don't remember, but Lagrange multipliers are your best way to go here for sure. I'm mentioning that you could use the second parcels test, but you don't want to. Yeah, any optimization problem on the exam, you should use Lagrange multipliers. But obviously you have to use second partials when we're getting, relative min, relative max, and saddles. But I'm talking about these ones that have optimal answers here. We don't want to use that method, because you may recall from the notes there I showed an example in the Lagrange of a couple of them that we did in the using second partials, and they were much more work. And that was the idea, was to show the beauty of Lagrange multipliers compared to the second partials for applications. All right, so we need the partial derivatives. So the lambda is going to go on the same side with the constraint here. So the left side is going to be each partial. So this is basically G in the definition. So basically it's F equals lambda G. Well, so in other words, Fx equals lambda Gx and so forth, so on. So the partial here will be of x will be y plus 2z. And then the partial of x, y, z, respect to x, will be yz, so the lambda goes right there. The next one will be x will be the partial of xy respect to y, 2z, so x plus 2z. This one respect to y partial will be xz. 2x plus 2y will be this partial right here, lambda xy. There we go. And so now it's you just solve it algebraically, however you want to do it. And you'll see this is the kind of the way I did it in most of my examples in the notes. So this one I'm taking, in other words, the first two, and I'm solving them both for lambda, which means I'm dividing both sides by whatever is multiplied by lambda. And that, in other words, that way you're getting like this. You're getting a lambda equals lambda, which means you can then set those expressions to each other. It looks like it's going to be complicated, but it turns out it's not. That's the beauty of it. So you kind of do a little cross multiply. Then look what happens. So these two x, y, z terms will just cancel, like if you subtracted x, y, z both sides. Now you look at this one, you could ignore the z squared. You can pretend, ignore that. So basically, x would have to be y. So it's like saying 2x equals 2y, which means x equals y. So that makes life easier. Now I could have compared the first one and the third one. I compared the second one and the third one, because we just did the first and the second. So I just did the second and the third. So once again, I'm setting lambda equals lambda by dividing both sides. So divide both this one by xz and get this, and divide 2x plus 2y by xy, cross multiply. So you see they both have a 2xyz, which can be canceled. And you can ignore that the x squared can also be canceled. So you're looking at y equals 2z. Normally in algebra, you're not supposed to divide by variables in certain situations because you lose 0 as a solution. But obviously, 0 can't be a solution to this problem, so it's really okay to divide by x squared. But that's a mistake people have to be careful of. Like if you had, let me just real quick go over and just take an equation like this. It's going to look kind of sloppy here. Sorry about that. And forgetting this wasn't an application problem, like right there, students will often make the mistake of just dividing both sides by x and saying x equals 1, which is only half right. X also equals 0. That's because obviously what you should have done is brought the x to the other side and then factored. But in these problems, so as I'm writing this sloppy looking here, I'm using a mouse instead of a stylus. Don't have it with me. No pen, so that's okay. It's not like this was that important anyway. But we can do that for these Lagrange problems. Or we can divide. I could divide by the variables, in other words, because let's say 0 is not a solution to the measurement problem. So that would yield 0 and 1. So it's just kind of a helpful math tip. I had to, want to be careful instead of just saying, "Oh, divide by the variables," But yeah, it's okay here, but not always in math in general. Okay, so I've got x equals y, and I have y equals 2z, so that means whichever the common variable, whichever order you pick, whatever the common variable is, in this case the y, that's the one we want to solve in terms of, not for, in terms of. So I already have x equals y, so now to take this, I take z in terms of y. So if I have x in terms of y, z in terms of y, we're down to one variable. So if y equals 2z, that means z equals y over 2. So there's your z. So now you take your constraint equation. X is now y. Of course, y is just y. And z is y over 2. And that gives you, bring the 2 over, multiply, gives you 64. Y cubed equals 64. That's easy, just y equals 4. So we know that x equals y, so x will also be 4, and z is half of that, so it'll be 2. So the actual dimensions are base 4 by 4 with a height of 2. And then to calculate the surface area, you just put in 442 into that equation right there, and that'll if it's asking for that. It may only ask for the dimensions, but if it wants the actual value, you just take those 442, plug them in, which I did right down here. There we go. That's easy enough. 48 square feet. Not too bad. Number 29. Oh, okay. I guess I hadn't looked at this problem when I was talking in the last one when I mentioned the question in the quiz. It's that, yeah, okay. So this is what I was just mentioning is the same kind of open metal box. I guess I could have, except now we're maximizing volume based on a given surface area. Yeah, I'm just going to put the picture back down here again. Not that it's needed, but what the heck. All right. Now, so we're maximizing x times y times z, and then here's the constraint equation. Same idea. It's an open box, so we only have one area on the base. The other ones are two because, two sides, one, and two opposite sides. But only one bottom, no top. So here's so the left side will be the partials of x, y, and z of the volume. So it'll be yz, xz, xy, and now we have the lambdas times the partials of the constraint equation. The x partial will be y plus 2z. The y partial will be x plus 2z. And 2x plus 2y will be the z partial. So same kind of idea as the last problem. So you just basically take a lambda equals approach. So you see I solved all of them for lambda. I didn't label, I didn't draw arrows this time, but we can figure it out. So you tell by looking at these two, I took the first two again. I usually take the first two. So it's the first one equals the second one. All right, so you cross multiply. You see you have the xyz common goes away. Similar looking kind of idea as the last one. And then you can kind of ignore the z squareds and the 2, and you get y equals x. And it looks like I took of course, there's the first one again, and now I took the third one. So I compared first with second, first with third. But I could have done second with third if I wanted to. As long as there's only 3 combinations, just pick any 2. Cross multiply. And then the 2 xyz's cancel. And then the y squareds go away. So you have x equals 2z. And so that means since whatever the variable in common, last problem it was y, here it's x. That means we solve for x, not x in term. So this x equals 2z then will need to be rewritten as z equals x over 2. So we go to our equation, our constraint right here. So y is x. So we have 2xz, 2x, x is z is x over 2, plus 2x times another x over 2 equals 30. You get 3x squared equals 10, 30. 3x squared equals 30. That means x squared equals 10. Now, mathematically, and we had this come up earlier with another problem with solving for relative mins and maxes. In that situation, you would absolutely have wanted both plus and minus. Very important for those kind of problems. You want plus and minus root for those. But here, because it's a measurement, it's a length, we only have to use the positive. We can ignore the negative root 10. Okay, so x is square root of 10. Y equals x is square root of 10. And z is the square root of 10 over 2. So there's the actual coordinates. Nobody said these had to be integer answers or whatever, so mathematically they can certainly be radicals. So the volume is just multiplying these 3 terms together. 2 square root of 10s together make 10, so 10 divided by 2 is 5, and then times that last square root of 10. Excellent. Don't know what this is. Oh. Get rid of that mess. Don't know what was going on there. Whatever I did, I'm sure I didn't mean to save that like that, kind of haphazardly, but all right, that's easily fixed. All right, let's see what we got here. Number 30. So the x partial will be 4, the y partial will be 6, and then that'll be 2x, so it'll be 2x lambda, 2y lambda, and then here's your constraint equation, x squared plus y squared equals 13. So obviously the idea is, we have 3 equations, 3 variables. We're trying to use these in any way possible to come up with the right answer. And this one's not too bad. So I'm doing, this time though, I'm not solving for lambda. I'm not doing the lambda equals. I'm not sure why I chose to do it this way. You could try it the other way. This works, but I'm not concerned about that. But you could try the lambda equals and see what happens. Yeah, why didn't I do that? I don't know. Maybe I thought it'd be fun to get lambda for a change or something. But yeah, that might be good practice for you. Try it the other way. Lambda equals. But anyway, so I did this. I solved for x and y. And this isn't that hard. It's not like I did something that took an hour that could have been done in 2 minutes. No, I mean, this isn't difficult, thank goodness. So I put in 2 over lambda for x. So 2 over lambda squared. 3 over lambda squared equals 13. And you get 9 over lambda squared, 4 over lambda squared, add them together, 13 over lambda squared. So here we got, now these aren't x and y, there's no application on this one. So you can assume it's plus or minus. In other words, there's nothing in this problem that says it can't be negative. Whether it's telling you that in the problem or common sense, meaning, the length of a side or something like that, a measurement. So that's basically the same thing as saying lambda squared equals 1, so lambda would be plus and minus 1. This didn't work out too bad this way, actually. So you take lambda equals -1 and plug them right in here. You'll get 2 over -1, 3 over -1, you get -2, -3. Plug in 1, you get 2 over 1, 3 over 1, you get 2 comma 3. Those are your 2 points. Now to identify minimum and maximum, what you have to do is... because a lot of times in the Lagrange multiplier problems, if you have one answer, then that answer for sure, and you did everything correctly, of course, that's going to be the optimal answer. Meaning, if it's supposed to be a minimize, it'll be a minimize. If it's supposed to be a maximize, it'll be a maximize. But in this case, extreme values mean we're looking for min and max. So we don't use second partials test or anything like that. All we do is take the 2 values, plug them into the original equation. So I'm showing you that f of -2, -3, right here, right there. 4x plus 6y is -26. The other one's positive 26. So the smaller of those two would be the minimum, the -26. The larger would be the maximum. There we go. Okay. So there's how you would handle that kind of problem where it doesn't have just one answer, and maybe there were 4 of these or something. If there were 4 of these, it's still the same rule would apply. The largest would be the max, the smallest would be the min. It is possible there could be a tie, so it could be max plural or minimum plural. But this one's pretty straightforward. Smallest is the min, largest is the max. Number 31. Let's see what we have. So we have our function here, x plus 2y plus 2z. So now we're throwing z in there to give us, so we're going to have 4 equations and 4 variables. Well, we're going to be okay. And there's my constraint, that sphere, or radius 1. And then the partials of these 3 equations are easy. They'll be 1, 2, 2. And this one's easy, 2x, 2y, 2z with the lambdas. So it looks like I did now back to the lambda equal. So I took the first 2, and that gives you y equals, cross multiply, gives you y equals 2x. And it looks like I took the bottom 2 this time. So usually I was taking 1 and 2 with 1 and 3, but I chose to do 2. That's not, it didn't matter, that's okay. 1 over y equals 1 over z will lead to y equals z. So since y is the common variable, we have to solve for y. So does that mean z equals y, x equals 1/2 y, or y over 2. So we plug it into the constraint equation. Now, here's the constraint equation on the inside in purple. It's y over 2 squared plus y squared equals 1. I decided to go ahead and immediately get rid of that's going to produce a 4, obviously, on bottom. So I wanted to get rid of the fractions after doing that. So y squared over 4 times 4 will just be y squared. Now both these individual y squareds will become 4y squared, and that 1 will become 4. So we come up over here, and we end up with 9y squared equals 4, and then y equals technically plus and minus 2/3, but that's okay. The idea is that you could plug both those in for y. It's okay if you do the plus and the minus 2/3, but I'm just mentioning that there's no way that in this particular equation here with x plus 2y plus 2z is that the negative will produce a maximum. That's not going to happen. So, but that's okay if you don't notice that. If you plug them both in. Yeah, now had this one been asking for find the all extrema, then yeah, we would have had a max and a min for sure. The negative 2/3 would have produced the minimum, but it will not produce the maximum. All right, so x equals 1/2 y. Oh, I'm sorry. So y is negative 2/3. A positive 2/3, excuse me, I just said not to use the negative. So 1/2 times 2/3 is 1/3, and z equals y, so it will equal 2/3. So your point is going to be x is 1/3, y and z are both 2/3, so that's your actual coordinate, and then the value will be, just plug it right into this equation, easy enough, and you get 3. So the minimum would have actually turned out being negative 3 if we'd have used that negative value for y. Now we have a Lagrange multiplier problem number 32 with 2 constraints, where we introduce the lambda and the mu. These can get a little crazy at times because there's just so many different ways you can go about it. But anyway, let's just look at the setup here. So there's your function. You're trying to find the max and minimum for this one specifically. So the partials for this one would be 2x, 2y, 2z. And then the first, it really doesn't matter which one you use for lambda and mu, that doesn't make any difference. But I just use the first one I see for lambda and the second one for mu. So this will be 3, the partial of x will be 3, so it'll be 3 lambda. And the partial for this one with respect to x will be 1, so it'll be 1 mu. The next one, the y partial for the first one's negative 1, so it'll be negative lambda. The y partial for 2 here is 2, so it'll be 2 mu. And for z will be 1 lambda. Z will be 2 mu. So it looks like I just went ahead here and solved all of them for x, y, and z. I just divided everything by 2, nothing special there. And there are 2 constraint equations. So we got 5 variables, 5 unknowns, and then you just kind of jump in there and see what you can do. Yeah. This one's actually, even though it looks bad, it's not that bad. Whenever they're kind of linear terms like this, meaning you don't have like x's and y's and stuff multiplied together. So here's the approach that I took. Because that looks really bad if you just sort of stare at it like that. But I think you'll see the approach makes sense. So I took x and y and z in terms of lambda and mu, and I'm substituting into my 2 constraint equations. And what that will accomplish is when that's all plugged in, said and done, it will reduce down to a system of equations with only two variables, lambda and mu. Now remember, we don't actually, so that's why with lambda, you don't have to get lambda and mu, the values for them, but sometimes to solve the problem, it makes it easier to do it a certain way where you actually find what lambda and mu are, even though they're not required answers. So I'm getting lambda and mu, and then you see from these three equations right here in the light blue, once we have the values for lambda and mu, then x, y, and z will be easy to get. So I'm just taking these three things and substituting them into these two equations right here. So you see I have 3x, there's the x, minus the y, here's the y, plus the z, here's the z, equals 6. Now, I'm already, and same thing for the bottom problem, so the x plus 2y plus 2z equals 2. I'm already trying to get rid of the fractions. So I have a big giant 2 here on the outside that I'm using to eliminate all those 2's on the bottom. Now, of course, it's going to double what's on the right side, though. Keep that in mind. Yes, it kills these three 2's, but 6 becomes 12, 2 becomes 4. Alrighty, so it looks kind of bad, but it's not that bad. So we're going to distribute the 2. The 2 is now gone, so distribute the 3. We have 9 lambda plus 3 mu. Distribute the negative, so that makes that plus mu lambda minus 2 mu. And then plus lambda plus 2 mu. The bottom one, 3 lambda plus mu minus 2 lambda plus 4 mu plus 2 lambda plus 4 mu equals 4. And then just kind of add the like terms up. That's easy enough. Just add the like terms, and you'll get this pair of equations over here. 11 lambda plus 3 mu equals 12. 3 lambda plus 9 mu equals 4. And then I multiply top equation by negative 3, elimination by addition. So that way when I add together, the mu's will cancel. So I'll have negative 33 plus 3 is negative 30 lambda. Negative 36 plus 4 is negative 32. Lambda equals, mu equals, all right, so lambda will equal 16 over 15, and then you plug the 16 over 15. I didn't actually show it here, but basic algebra. If you plug the 16 over 15 into either one of these two equations for lambda, whatever, the bottom one or whatever, and you can solve for the mu, and you'll get 4 over 45. And like I was saying earlier, you take those equations I had back up there in blue, right here, and now we just plug in the values for lambda and mu. So 16 over 15, 4 over 45. I got 74 over 45. Negative 20 over 45, and 28 over 45. I mentioned may not be. Well, I don't think there's much by hand. I say there may not be, but I don't think there's an easier way to do it manually. Now, here is, if you want to use matrices in the calculator. I did that in the example for this section. And the important thing for this is that everything is linear, meaning you don't have like x times y multiplied together, or x squareds and z. They have to all be, lambda and mu are going to be linear, but x, y, z have to be x, y, z. They can't be like, z times y or anything like that. So, and frankly, I would, with these two constraints, one constraint, that's different. Two constraints, I don't think I would put one on a test that was nonlinear. So I wouldn't worry too much about that. There might be one coming up here, I don't know, we'll see in a minute. But I'm not going to worry about it too much. This one, you take those original equations, like so, and you line them up an x, y, z, lambda, mu. Well, the order is not, well, whatever order you put them in, just make sure you realize that's the order that the answers are going to come out. So essentially what I did with these first three is brought everything over to the left so I'd have 0 on the right side. The bottom two are already set up. You know, they need to be equal to whatever, some number. So these are happen to be zeros, of course. So you got 0, 0, 0, 6, 2. And then I'm lining up the coefficients for a visual. So you see how they all line up. And I just wrote it out as a matrix. The matrix just coefficients. Anywhere you don't have something, it's going to be a blank. And I believe I showed how to enter it in the matrix in the calculator, but you know, you can Google that and find that a YouTube video, super simple. Will tell you, oh, how do I enter, you know, entering a matrix into a calculator kind of thing. It'll show you. So I'll skip that for now. So I probably did it. Hopefully I did it in the notes. But you can look that up easily enough. Yeah, so you see everywhere you're missing something, you just put a 0 in the matrix like so. So we have to enter this matrix 5 rows, 6 columns. You know, even though that line there is just visible, it's just to sort of separate it. But when you put it in the matrix, so the actual matrix, the line's not really there. You know, it just means that's the last number in each row. So it's 5 rows, 6 columns. So it always goes 5 by 6. And I'm showing the commands here. So once you go math, RF, and you'll go to names, back to names to bring your matrix A in. Names, matrix A, hit enter. And of course, put it in decimal. So you see what I did. I went math frac, so we could see the frac answers there. And there they are, same answers. We got X, Y, and Z. And there's the lambda and mu, which, you know, you don't really have to have the lambda and mu. It's just the way I worked it out. We got it. So if you were going straight to this matrix method, you wouldn't even need the lambda and the mu. You'd have the X, Y, and Z right there. There you go. So you could do either method. Let's take a look. Now we're back to one with one constraint, no problem. Box and an ellipsoid. That one's in my notes, so you can go back and look at that. It'll fall, it'll be exactly like that. So what I did is, just like the notes, we worked with just the first octant, everything positive. So X, Y, Z positive, but that means the shape will have 8 equal sections. And so just put an 8 in front of this, and there's your constraint. So the partials then will be 8y, z, 8xz, 8xy. Then we got a 4x, a 2y, and an 8z with the lambdas. And so I just basically did a lambda equals lambda approach, cross multiplied. Now this one, now notice the equations, the variables are all x squareds here. So what I did was when I got to this point right here where I have y squared divided by 2 and y squared equals 2z squared, 2x squared, I didn't bother taking the square root. There's no point because the variables are already squared right here, so you'll be able to plug them in that way. So there's no point in taking the root. So you do this bottom one, and let's see, same kind of idea. So there I did 1 and 2, and I did 2 and 3. And I get 4z squared equals y squared. So normally at this point I would tell you to say take x squared and solve in terms of y squared, and z squared in terms of y squared. Normally I would tell you to divide by 2 and then divide by 4. But if look at the equation, it's conveniently worked out. It's already has it as, I mean, you could do that, but if you notice that y squared equals 2x squared, so you can just put y squared there, and you have 4z squared equals y squared, so you got a y squared right there. So that worked out real nice. You have y squared, y squared, y squared. Add them together. So you got 3y squared equals 12. y squared equals 4. And once again, we're ignoring the negative solution. We don't need it. So y equals 2. And then I know that that means, so 2 squared, 4 would equal 2x squared. X squared will equal 2. So x will be the square root of 2. And then for the last one, 4z squared equals y squared. So y squared, y is 2. So 4z squared equals 4. Z squared equals 1. So z would just be 1. And then it will yield square root of 2 as x, y is 2, y is 1. That's the optimal point in the first octant, and then it would go all the way around to all the negatives around the, centered at the origin, and that gives you the maximum possible volume of 16 square root of 2 for the entire thing. Okay, number 34, we're trying to find 3 positive numbers whose sum is a maximum. So clearly positive here. So there's the function we're trying to maximize. Here's the constraint. So the x partial will be 2xy cubed z. And the y partial will be 3x squared y squared z. The z partial then will be just x squared y cubed. And then the x, y, z partials for constraint would all be 1s. So you have lambda, lambda, lambda. And then the bottom constraint, x plus y plus z equals 36. So 4 variables, 4 unknowns. Let's do it. So we're just going to kind of go with them. So 1 and 2, I'm doing a lambda equals lambda thing. So I'm setting these two equal to each other. I divided out the z. Once again, these must be positive numbers. So I am allowed to divide by variables. As I said in that earlier example, you can divide by variables here when you know they're positive. So I get, and then, okay. So I didn't show it here, but if you divide both sides by x, you'll kill this x and leave an x on the right side. And if you divide both sides by y squared, you'll get rid of the y squared on the right and you're left with a y. So you have 2y equals 3x. Okay. And then I worked with 2 and 3, same kind of idea. I took these two. And then x squared divides out. And then same thing, if you divide both sides by y squared, you'll get 3z, and then you'll have a y left on the right. So you have 3z equals y. So now we need to solve everything in terms of y, because it's the common variable. So that means x would equal 2/3 y, and z would equal 1/3 y. So not too bad. We go back up here. And so there we go. So x is 2/3 y, y is y, z is 1/3 y. Add that up together, you got 2/3 and 1/3 1, so it makes it 2y when you add that up equals 36. So y equals 18. 2y equals 3x. And from right up here, so we know that y is 18, so 2 times 18 equals, I guess I could have just said that, well, yeah, okay, or you could have just said x equals 2/3 y. Either way, same thing. X equals 2/3 y, but anyway, same answer. 2 times 18 equals 3 times x. You'll get 12 for x. Same thing here. I could have said z equals 1/3 of y, so it's going to be 6. But that's okay. 3z equals 18, z equals 6. So you have 12, 18, and 6, meaning those three numbers add up to 36, and there's no other possible combination of positive numbers that add up to 36 that will make your value here to be larger. Yeah, this one I didn't actually ask for what the value would be, but it would actually be quite large. So yeah, that'd be kind of, I mean, you'd be using a calculator, so it's not that bad. But wow, yeah, the maximum value would be 12 squared times 18 cubed times 6, which, wow, big number. I mentioned when I did the two constraint problem that I wasn't sure. I scrolled down here that I mentioned that it would absolutely be on a test. I might have done one in my notes. That's what I was thinking of, where it got a little dicey there, but it would be a linear one, meaning that you could use matrices if you wanted to. I didn't put a nonlinear here because I knew I wasn't going to test on that or whatever. So, but the ones that are nonlinear with lambda and mu can really get kind of ugly, and you can't use matrices on them. But no, so okay, so I just want to clarify that because I wasn't sure if that was coming up or not, but it did not. So then I pretty much did what I usually do on a test, is not include the nonlinear two constraints. So, well, all right then, that concludes the second part of the solutions for exam 2.